Okay, day 8, warm up and lesson on the same page. So we'll just do them both. So pause the video, try warm up problems 1 through 4. Show your work. Multiple choice does not mean no work. It usually means more work than non multiple choice. So pause the video, try them, unpause it, and I'll show you what the answers are. Okay. You tried them. Answer number 1 is B. The answer number 2 is D. The answer number 3 is B. The answer number 4 is B. So I'll show you the work. So this one we're finding G prime and 4. So the first thing to do is to find G prime using the power rule. The one derivative rule I think I've taught you. You multiply the power in front. Yep, 4 over 32 is 1/8 x cubed minus 10x to the first. I'm going to plug 4 into this. And so it's going to be 4 cubed minus 10 times 4. That's going to be 64 over 8 minus 40 is going to be 8 minus 40 is going to be negative 32. There you go. Number 2, we're finding the domain of this function. So that means the inside needs to be greater than or equal to 0. I think it would help to write it negative x squared plus 4 is greater than or equal to 0. We could divide negative out of both sides just to make it a little more like standard form. You don't have to do this, but you got to flip the inequality symbol when you do that. So then we'd factor it, x plus 2, x minus 2, and get the roots, and then do a line check. These would be solid dots at -2 and 2. Test a value. X equals 3. Positive times positive. Positive is false. True, false. And so your domain is -2 to 2. Brackets, or you could write it like that. And that's another way of writing it. Number 3, the equation of line tangent to a curve at x equals 3. Well, you need a point. So we have half of the point. We have the x value of the point. We need to find the y value of the point. And so we're going to get 4 times 27 is 108. Minus 9 times 7 is, did I make a mistake? Let's see. 9 times 7 is 63, is going to be 45. And so the point on the graph is 345. Then we need the slope, which comes from the derivative. So we've got to do y prime, power rule, 12x squared minus 14x. Then we want the slope specifically at x equals 3. So we plug 3 in. And we get 12 times 9 is 108. Minus 3 times 4 is 42 equals 66 is your slope. And so you have everything now to write the equation line. Point slope form y minus 45 equals 66 times x minus 3. Point slope form is good enough for free response, and it is good enough for multiple choice if it's on there. So that's it. Number 4 says bonus. That doesn't mean optional. That means bonus as in like, yay, I get to do another problem in the warm-up that's challenging. If the function is differentiable, which by the way, remember also means continuous, got to be continuous to be differentiable for all real values of x, then b must equal what? So continuous is if you plug 1 into these, plug 1 in, you get 3a plus 2b plus 1. If you plug 1 into the other one, we get, I'm just showing all my work here, we get a minus 4b minus 3, and then these should be equal to each other. So there's one of your equations. So continuous, that's continuous. The y values have to be equal to each other at the transition. They got to be connected to be continuous. So then, we go write this a little nicer. We could say, all right, well, that's 3a plus 2b plus 1 equals a minus 4b minus 3. And it might be nice to clean this up, move all the a's together, move the b's together, and maybe move the non-a b's to the other side. So this would be 2a plus 6b equals -4. So that's one of our relationships. This is a system of equations. There's two unknowns, a and b. X is known, x is 1. So we need two different equations to solve the system of equations. So differentiable means that, one, it is continuous, but also that the slopes are equal at the transition point. So we got to find the derivative. And remember, a and b are just letters for numbers. The x is what we're doing. We're doing power rule. It's going to be 6a x to the first plus 2b. And derivative of 1 is 0. And the next one's going to be 4ax cubed minus 8bx minus 3. And then so when we plug 1 into these, we get 6a1 plus 2b is 6a plus 2b. And 4a1 cubed minus 8b1 minus 3 is going to give you 4a minus 8b minus 3. And then these are supposed to be equal to each other. So that gives you 6a plus 2b equals 4a minus 8b minus 3. Now we can clean this up. Maybe get all the a's together, get the b's together, maybe leave the non-a b's on the other side. We get 2a plus 10b equals -3. Now, to solve this system of equations, you could use substitution, which is kind of usually the method I use. But since both of these equations are nice linear equations with a and b in them, there's another process called elimination, which I find to be very convenient here. So you can subtract one equation from the other, add them, multiply them first, then add them, so that one of the letters drops out. The whole point is to hopefully get a letter to drop out. So we got to distribute that negative, right? So that's going to be, those are going to cancel. This is going to be -4b. This is going to be -1. So b is going to equal 1/4. Done. Now, if you wanted to, you could also find a, or maybe they ask you to find a. So then you would plug this back into one of those equations and you'd solve for a. Not that you need to, but this is what you would do. You'd say like 2a plus 6 times 1/4 equals -4. You might choose to get rid of the fractions, multiply everything by 4. You get 8a plus 6 equals -16. 8a equals -22. A equals 11/4, -11/4. So that's what a is. Not that you had to find it, but you could have found a first, just if you weren't trying to specifically find b. I wasn't really trying. That just worked out really nice. So that's the work for that problem. And this is some good kind of review for your test coming up. This is going to be our last lesson of the unit, our 6th and last lesson of this unit. So we got to do a little more conic sections. We did parabolas. I brought up circles and hyperbolas, I think, on a warm-up. But let's do a little more thorough talk about conic sections and what to expect in my class as far as those conic sections. You've probably done more work on conic sections in previous classes than I even need. Now some of these functions, so we talked about before, I showed you guys this little diagram that if you do two cones upside down and you cut it with a plane in different ways, you get these different conic sections. If you cut it perpendicular to the axis of rotation or symmetry, you get a circle. If you tilt a little bit, you get an ellipse. If you tilt it more, you get a parabola. If you tilt it more, you get the hyperbola. So some of these are not functions. And that's going to introduce some interesting things. So circles are not functions, ellipses aren't functions, hyperbolas aren't functions. Now parabolas are functions. A point, a line are a special case of conic sections, I guess, kind of silly. But some of these are not functions, okay? Anyways, usually if they're not functions, they get restricted to just half of their shape so that they are functions. So here's the sort of the general equation for a circle: 8x minus h squared plus y minus k squared equals r squared. H is the horizontal shift, k is the vertical shift, and so the center is typically at 0, 0, but if you do any shifts on it, this is going to be the new center. Shift it up, or shift it left or right, shift it up or down, you get a new center. The radius over here is squared. Now, I'll say that usually on, this is a special case where the center is 0, 0, and I'll say probably most of the circles we're going to sketch are going to be centered at 0, 0, which is nice because a lot of times circles aren't in this form, and to get them in this form, you have to complete the square twice, and for whatever reason, you guys seem to really not like completing the square, but it's something you learn how to do in Algebra 1, but you probably do it again in Algebra 2 and pre-calc. But, then you have the radius, and there you go. Now, this is not a function, right? Fails the vertical line tests. Every input has 2 outputs, most of them. But we'll talk about how that gets taken care of. All right, this one, do you recognize that this is actually the equation of a circle? I know this is the way we usually write equations of circles in previous classes, but most functions that we study, we solve for y by themselves. What maybe the best thing you could do is when you see something like this with the square root and the x squared inside is think that's probably some kind of conic section. So let me rearrange it to make it look more like what I'm used to, and then I'll be able to tell for sure what it is. So we would square both sides. You get y squared, and the negative gets squared and goes away, and then you get 25 minus x squared, and then you get add x squared to both sides. And so then we have x squared plus y squared equals 25, and that looks a little more familiar, right? The radius is 5. Now, when you go to sketch it, don't do the whole thing yet. Just, follow along with me because there's something important going on here that you're going to miss. So we're just going to do it lightly first. So this is a circle centered at 0, 0 with a radius of 5. And so usually I go up 5, left 5, down 5, right 5 when I go to sketch a circle, or even kind of the same idea for ellipses. Here's the deal. Is it the whole circle? You're like, yeah, sure, why not? No, it's not. Now, if I gave you this, it would be the whole circle. We changed this to make it easier to draw or recognize. But the original problem just had a minus. If you were to try and solve for y equals by itself, from this, you get plus or minus the square root, which would be the whole circle. The plus square root is the top half, the minus square root is the bottom half. But what we started with is the bottom half, the negative, the bottom half. So our sketch for this should only be the bottom, okay? Solid dots. That's it. Okay, and now, by the way, a nice side effect of this is it is a function now. It does pass the vertical line test if you only take the bottom half or only take the top half. So anyways, be careful. The way it was originally written has some key information there that you kind of lose if you change it to a different form. Okay, so that's a circle, and not necessarily in the form that you would usually recognize it. And I'll be honest, if I looked at it right away, I'd be like, is that a circle or hyperbola or ellipse? Or I don't know. Let me change it real quick, and then I'd probably do that because I remember really well from the ways that we learned them. Now, here's an interesting problem. and I'll just let you know, we will have a problem like this on your next test, so I'd pay attention. It says, find the slope of the tangent line to this graph at this point. So let's do a quick sketch here. 5, 5, 5, and 5, -5. And so now, is this a whole circle? Is it just the top? Is it just the bottom half? This is the whole circle. This is the whole thing, which means it's not a function, but that's okay. We're going to do some stuff that doesn't require it to be a function necessarily. So that's the whole graph, right? Now, it has a radius of 5. Now, it says that we want the slope of the tangent line at -3, -4. Now, there's lots of tangent lines all around this graph. At -3, 1, 2, 3. So -3, 1, 2, 3, 4, -4 would be like right here. And it should look like it's probably close to the edge of your circle. So that's, I'm going to draw that. Now, I'm telling you guys this is going to be the best way to do this is with a picture, but I'll show you some ways to do it without a picture in a second. But this will be the way, at least for now. Maybe even when I teach you guys some other stuff, you still might want to do it this way. The tangent line is something like this, right? So you're trying to find the equation of the tangent line. This gives you at least a basic idea of what the equation should look like. It should have a negative slope. It should have a y-intercept that's way down here if we bother to put it into its slope-intercept form. And by the way, we're just looking for the slope. We're not looking for the equation. So we better get a negative answer, essentially, right? I mean, that's one key thing. Now, so this strategy, I'm going to teach you 3 different ways. So we're going to leave some room over here because I'm going to teach you 2 other ways of doing it. So the first way is just draw a picture and use geometry. No calculator, no real calculations. Okay. Now, there's this key thing that you guys learned in geometry about circles and tangent lines and circles. You learned all kinds of stuff about circles and geometry. So there's a special thing about a tangent line to a circle, something that's always true about it. Can you remember? It has something to do with the radius at the point of tangency. There's something always true about the radius there and the tangent line. They form a right angle. The perpendicular is perpendicular to the radius at that point. So we're going to rely on that because that's going to make this really easy to figure out. So you guys know how, perpendicular lines, their slopes are negative reciprocals, right? So what's the slope of the radius? We should be able to find rise of run because we actually have 2 points. We could even just count it. It's up 4 over 3, positive 4 over 3. It's definitely positive, up 4 over 3. So then the perpendicular slope to that, which is the slope of our tangent line, is the negative reciprocal of it, -3/4. There you go. So that's a quick, easy way. That doesn't really use calculus. Now, there's ways for us to do it with calculus. Okay. Now, we've talked about that the slope of a curve is the derivative, right? But here's the deal. Can you take the derivative of this? I don't think so. Like with all these extra variables and stuff, it's going to use something called the chain rule, which I don't know. Maybe they teach you in pre-calc, but all the people who took pre-calc, I'm sure, forgot it. So we're going to have to use something called the chain rule, but we haven't talked about it yet. Now I'm going to just show it to you. I don't want you to use it yet, okay? I don't want you to use it until we teach it, official, okay? So anyways, there's 2 more ways we're going to do this. So one way is to then get this equation into y equals, because that's usually what we do when we take derivatives. So you would subtract x squared, right? And then you would take the square root of both sides, plus or minus. Okay? Now, is it both of these? Do we need to do both? Is it the top half or the bottom half? You're like, it's the whole thing. Yeah, but where's the tangent line that we're concerned about? Oh, it's the bottom half, right? The whole graph is involved in this problem, but we're really just interested in the bottom half because the point they gave us is definitely in the bottom. By the way, without a sketch, you would know this is in the bottom. This is on the bottom half of the circle because the x is negative and the y is negative, just because the y is negative. So that's why it's the bottom. Now I would rewrite this. Negative, I'd put parentheses 25 minus x squared to the 1/2 because square roots are actually powers. They're rational exponents. So we actually use the power rule that we've been using. So that's not a new thing. We would multiply the 1/2 in front. Now here's the weird thing. You're like, well, what do we do with these parentheses? You keep them. You leave everything inside. And so you multiply the current exponent in front, and then you subtract 1 from that exponent. That's the power rule. But here's the chain rule. The chain rule says, okay, now you need to take the derivative of what was inside, which is derivative of 25 is 0, minus x squared is minus 2x. That's what's called the chain rule. Now we could try and clean it up. The 2's cancel each other out. The negatives cancel each other out. Probably want to rewrite it in a more friendly way to do work with. So the x is on top. A negative exponent means it's in the bottom. And a 1/2 is square root. So this is a square root of 25 minus x squared in the bottom. So this is your derivative, okay? And then we could go ahead and plug x equals -3 into it, wherever we see x's. And so we get -3 over the square root of 25 minus 9, which is 3 over the square root of 16, which is -3 over 4 for the slope of the tangent line. Hey, it came out the same. That's good, right? Now, the reason I don't want you to do it this way, one, is it involves a rule that I haven't really officially taught you yet, so I don't want you to use it. Two, even if you knew that rule, which one was easier? This one was way easier. And I'm all about like, let's do the easier way this year because we got to be fast. It's not always the best idea to do things the most technical, thorough, regular way. Because if it takes a long time, no, that doesn't make sense. On the AP test, you have time restrictions. On my tests, you're wanting time. Now, by the way, this was called explicit differentiation, which is the type of differentiation means taking the derivative of something. So that is the thing that we've been talking about so far, is taking explicit. But there is another way that I'm going to teach you even later after chain rule. It's called implicit differentiation. Now this is good just because this gives you a little peek at what we're going to learn, which I think is helpful to see these things a couple times before we go into it super serious. Okay. Now implicit differentiation says, you know what, we can take the derivative of something even if it doesn't have y by itself. So explicit means that you get y equals a bunch of stuff, then you take a derivative. Implicit, explicit is like straightforward, super clear. Implicit is kind of like a roundabout way of doing something. So here's the deal. We can take the derivative even when it doesn't have y by itself. The derivative of x squared is 2x plus. Now, how do we take the derivative of y? Well, it would be 2y to the first power, okay? But y itself is a function of x, isn't it? Like this y is the same y that we got right here. So we know that it's a chain rule issue. It's like it has a function inside of it that we ignore first, and then we multiply by the derivative of what's inside. Now, if we haven't bothered to write it like this, then what do we write? Well, we just write dy dx equals derivative 25 is 0. Now dy dx is your derivative. It's the same thing as y prime. I'm just scared to use y prime here because I have a y with a 1 power here. And in the middle of my work, I might think about why the one power is a prime or vice versa. And so when I do this implicit style, I use dy dx for the derivative just because it makes me feel better. So then we're going to solve for the dy dx. Subtract 2x from both sides, divide both sides by 2y. Dy dx equals negative x over y. So that's your derivative. So then how do we find the derivative at x equals negative 3? Last time we plugged in x equals negative 3. Now the weird thing here with implicit is that a lot of times it's going to have x's and y's inside of it. You're like, well, what do I do with that? I know what to do when I plug in the x. Well, we have an x and a y, right? So this is going to go in there. This is your y value. That's going to go in here. So it's going to be negative 3 over negative 4. And that's going to give you negative 3/4. Hey, what do you know? It worked. So anyways, 3 different ways of doing the same problem. This is the way you want to do it, this chapter for sure, just because these involve some calculus stuff that you're not good at because I just showed it to you for the very first time. I'm not going to ask you to do it on any of your homework. Do it this way. Use the geometric approach. And even in future chapters, after you get good at these methods, that's way more work, way messy, and easier to make mistakes than just draw a quick picture of a circle and use the slope of the radius to find the slope of the tangent. That's fast. Okay? All right. Ellipses are another conic section, and a lot of times this is sort of the way that we've written their equations. They're like circles, but it's like they got a longer radius in one direction than the other. And so instead of putting the r squared over here, they just put a 1, and they have the divided by a squared to b squared. These are like the radius, but there's 2 different numbers in 2 different directions. Now, at first, I might give you something that doesn't make you think anything of an ellipse or even a conic section. And so you might want to change. So we could square both sides. Y squared equals 36 minus 4x squared. You can bring the 4x squared over here by adding it to both sides. And at this point, you should recognize, oh, this is an ellipse. Because if there's a different number in front of the x squared or y squared, if they had the same number, then you could divide them both out and get over here and have a 1x squared plus 1y squared equals a number squared. That's a circle. If they have different numbers, then it's like a circle being stretched in one direction. If there was a minus here, that's hyperbola. So we're going to, so now that we know it's an ellipse, we actually want a 1 over here. So we're going to divide everything by 36. And it's going to be x squared over 9 plus y squared over 36 equals 1. And so this number squared, that's 3 squared. This is 6 squared. The center is at 0, 0. And then this tells you how far you're going to go in the x direction. 1, 2, 3. 1, 2, 3. And this is how much you're going to go in the y direction. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then what I usually do is I could draw a box and okay. So and then you can kind of draw it to kind of fit it inside of it. Okay, and so, and then is it the whole thing, or is it just the top or bottom? It's just the top half. So I should have drawn it more lightly, but it's just the top half. Okay, and so there you go. Might want to label these values on here. So, anyways, here's an interesting question. What's the area of an ellipse? So the area of a circle is pi r squared, and that's thanks to Archimedes, great Greek mathematician. And so, you know, and here's sort of a kind of interesting way of interpreting that. is that the radius squared is a square with sides r. And so we want 3.14 of these squares to make up the area of a circle. Okay, the area of one of these squares is r squared. Now, for an ellipse, we often use these little a and b values to represent the sizes. And like I said, we could sketch this. And it looks like that. This is the whole, I'm doing the whole thing right here. And so here, it's like we have these areas of these rectangles, and it actually works like this. It's 3.14 of these rectangles that make up the area of an ellipse. So the area of an ellipse, it's very similar to the area of a circle. It's pi. Here was r squared, r times r. Here it's going to be pi times ab. The area of one of these rectangles is a times b. So that's the area of an ellipse. So kind of interesting, related to circles. Hyperbolas are usually written in this kind of form. They look a lot like ellipses, but they have different signs. And the negative could be with the y squareds or the x squareds. And a lot of times we write the negative as the second one. And then we usually write this as a 1 over here. Now here's an example of one that's written with y by itself. So when I look at these and I see this y equals the square root with x squared inside, I'm thinking, oh, that's probably a conic section, circle, hyperbola, ellipse. So then I just try and, now the negative gets squared and the square root goes away. And then we really probably, it's usually nicer to have the first term be positive. So we're going to do the minus 4x squared here. And so at this point, you should recognize, okay, this is a hyperbola. Now, they could have the same number in front of them, so it could look a lot like a circle, but they have a different sign here. So we definitely need a 1 right here. And so we're going to get y squared over 16 minus x squared over 4 equals 1. So this is kind of like the way we're used to seeing it. Now, the way you graph one of these, it's centered at 0, 0. This one is. And then this is 2 in the left and right direction. This is 4 in the up and down direction. So this is like an ellipse. So I would put those out there. 1, 2, 3, 4. 1, 2, 3, 4. And so then I would draw a box just like I do with an ellipse. And you could also do this with circles. But for a hyperbola, what we do is we connect the corners of this rectangular box with a light dashed line. And these are actually slant asymptotes. So instead of vertical asymptotes, horizontal asymptotes. Then the graph's either going to be a U up here and a U down here, 2 of them, or on the left and right. So if it's X is positive, it's going to be left and right. If it's Y is positive, it's going to be up and down. So this one's going to be up and down, but, and I'm going to draw these lightly. They kind of look like parabolas, but they're different. They go towards these asymptotes, which should be drawn. And yours should look like they're going towards the asymptotes, not away from them, not crossing them. That's when an asymptote, it gradually gets closer and closer, but it is only the bottom part of the graph because of the way it was originally written. So this is going to be the darkened answer here. And we should put arrows on the ends because they go forever. And this point right here is 0, -4. That they call that a vertex, and there's another vertex up here. So whichever one is positive tells you if it's up, down, that's y direction. If the x's are positive, then it's left, right, because it's in the x direction. And so there we go. Direction of opening vertical is when y squared is positive, and horizontal is when x squared is positive. But you got to also make sure that you have a +1 up here. If that's a -1, then you don't quite have the right idea yet. So try the assignment. There's a bunch of sketches like the ones we were just doing. Some domain problems, which is review for you guys. At least one of those problems, like in the notes today, where you're trying to find the slope of a tangent line to a circle, and also some other log inequalities, which we haven't done before. So try those out. This was our last lesson of Unit 3.